So for our next speaker, we have Zhijing Jin. She's an incoming assistant professor of computer science at the University of Toronto. She's a faculty member at the Vector Institute and a Canada CFAR AI chair, and Ellis advisor and faculty affiliate at the Schwartz-Reisman Institute in Toronto. She co-chairs the ACL Ethics Committee and the ACL year-round mentorship. Her research focuses on causal reasoning with LLMs, AI safety, and multi-agent LLMs. She's also received a number of awards, including Rising Star Awards, Best Paper Awards at NeurIPS, and PhD fellowships and a postdoc fellowship. And her work has been featured in Chip Magazine, Wired, and MIT News. Please join me in welcoming Zhijing.
Thank you so much for the warm introduction, and also really happy to be here in the Evado workshop. So today I have a slight change of focus, given that tomorrow Joshua will also cover more about causality in science as a way to achieve AI safety. So I decided to talk more on our lab's work of LLM agents for causal reasoning in science. This talk will be relatively rich in content. We might cover around 7 papers in our lab, so we will just bear with the rich content. So as we all know, there has been a large use of LLMs in many domains, such as code generation, as Graham covered yesterday, robotics, also as mentioned in the previous talks and panel, decision making, and also computational social science. So, however, a key question behind is that we might face some reliability problem in that we might see accidents of LLMs suggesting gluing pizza and eating rocks. And the background of these mistakes come from, in one case, it's a hallucination in the generation, where they mentioned that to make the cheese stick to pizza more, just add some Elmer's school glue. And the other case could be that they're actually looking into some websites. So if you look at the query, tricky query in this accident about the user trying to ask how many rocks should I eat, the AI actually suggested 1 rock a day keeps the doctor away. And this one is actually not just a hallucination problem, but also if you look into the website, it's a RAG thing where they went to a website and found such suggestions. And the problem here might just be that the Onion as a website might not be used to generate the AI summary. And then behind these, we face causal questions, such as, is eating a rock really a cause for health? And to take one step further, as many of us know, when LLMs receive a question, the common mode is direct generation, where we trust it in commonly known facts, RAG, where we trust it in maybe document-based scientific questions and so on. And then lastly, we also see the rise of structured formal reasoning into LLMs. And some examples have been shown on the wide success of, and each of these modes have their pros and cons, in that the first mode is the cheapest one, but face hallucination problems. The second mode is seemingly reliable, but to judge what is the right source to trust, we inevitably still have to do a reasoning problem. And then lastly, we have seen the rise of a lot of reasoning capabilities of LLMs. And previously, we have seen success on maybe mathematical reasoning. For me, my personal example to show the growth of LLMs is always querying it a simple arithmetic problem, but change the number to a weird number such as 17th. And then we do see LLMs providing step-by-step solution before deriving at the right answer, which also uses a tool to ground the calculation. And then to migrate this further, we really want to ask the question, now that we try to add the skill set of an ensemble of skill set to these LLMs with both direct generation, website lookup, and also is it solved by adding simple mathematical reasoning into it, and such as looking into the data better on the user query. And then I want to use an example to refute the idea of directly adding pure data analysis and the general simple mathematical skill, in that if we do want to answer the query of should we eat more chocolates, and then a data analyst will come up with the idea that, OK, we collected the data of chocolate consumption per country and the number of Nobel laureates, then we see a linear correlation with a very small p-value showing there on the top left. But then, as we all know, this is probably not the direct truth. And then this phenomena is even exacerbated by website lookup, where there could be some less reputable websites showing that eating chocolate leads to produces more Nobel Prize winners. And then if we say that we should defend it by looking into the source of the website, we might still see cases where it can be a Forbes website and a commentary mentioning chocolate and Nobel Prize has a causation. So how to solve this when all of them can go wrong? Our motivation really leads to causal reasoning as a solution. And the main bit here is that a good data analysis can lead us interpreting data in the past by formulating all these regression and modeling. But causal conclusions let us act towards the future. And also, as early as Aristotle time, we have been emphasized the necessity that we do not have the knowledge of a thing until we have grasped its why. That is to say, its cause. And then here, to ground the causality to a scientific level, as mentioned in the talk, we ground it to the mathematical expression of causal graph, one of the most popular branches of causal formulations, which consists of nodes as random variables and direct edges indicating causal links. And then putting them in each of the queries, namely, does chocolate cost Nobel Prize? Questions on this direct causal link, whereas the answer might lie in things such as there might be a confounder, like socioeconomic level of a country that leads to chocolate consumption and leads to Nobel Prize production. And then with this, we have seen great research agendas since one or a bit over close to 2 decades ago from my PhD supervisor, Benhard, and also Yosha has an amazing agenda on causality for machine learning as well. And then my work since several years ago has always been on causal NLP, namely to bring all these core ideas to understand and improve natural language processing models' causal reasoning ability. And then for that, we need to take one step back and think about what exact roles can LLMs serve for causality. So I used 2 example questions for us to have a motivation. The first one is, if we ask a simple question, why is the ground wet today? And then we're pretty confident that the current day LLM can tell us a list of potential causes, such as it has rained, maybe the sprinkler has been turned on, and so on. And then in the second case, if we come up with a more scientifically grounded, complex question, such as, does increasing minimum wage hurt or help the employment rate? Then we might see various answers grounded in economics and so on. And then the answer to this exact causal question leads to a Nobel Economics Prize in 2021. And then what we want to reach is, now that LLMs has a great pool of common sense, but how can we further guide them to answer a question that needs scientific insight, that needs data collection, and further analyzing the data from the causal perspective. And then also just as a coverage, we do have a list of work on common sense causality before, and also a survey published last year covering 200 plus papers that has been existent in the NLP community for many, many years on different types of common sense causality. And then moving further, today's talk is more about how to let them find the causal relationships on the level of data-driven, scientific thinking, analysis-driven ones. And then here, we have to take one step back and then think about, go over the main causal inference tasks that the statistics community, the broader experimental design community has been looking at. So the first task is on causal discovery. If we ground everything in the causal graph, causal discovery queries what variable affects what other, namely the existence of certain edges. Whereas causal effect reasoning asks for, given the graph, can we further get some more detailed information, such as the strength of the influence of X variable on Y? And then to map them to some natural language examples, maybe the first one can be if models have seen a lot of successful people's biography, should it conclude like lots of tech company CEOs are college dropouts? Does it mean dropout causes job success as a binary relation identification? Whereas the second one is more quantitative, namely such as how much does COVID vaccination increase the survival rate? And then they correspond to our earlier papers on core to cause and the CLadder, climbing the causal ladder. So just to give a brief overview of core to cause, and then we'll have a longer time of the talk on the quantitative causal reasoning from CLadder and on. So in this, can LLMs infer causation from correlation? We look into cases such as to distinguish correlation and causation. It's very common for models to see a lot of common sense data sets or news articles. Maybe there could be such a sentence as ice cream sales increase, the rate of shark attacks sharply increases. And then what should the model infer? Hypothesis 1 is that maybe ice cream makes the swimmer taste better. Hypothesis 2 can be that there is a hidden confounder of warm weather leading to more ice cream sales and also more more shark attacks. So moving this further, we again go to the formalism of a causal graph and plot them as 4 variables, A, B, C, D. Then the so-called correlation does not mean causation actually is grounded in graphical notations. First, nodes connected in the same causal graph may be correlated. The correlation is especially obvious when, let's say, B and D together have a common ancestor, and then this ancestor passes on correlations to both branches. And then, however, to conclude causal relations, then we either have to do interventions, let's say, to remove this, and then give people more, I don't know, swimming pool discounts, and then see whether this branch will be intervened. Or there are causal discovery methods that can help us judge from the correlational information, such as if we try to conduct things like conditional independence tests and a bunch of other statistical procedures, we will be able to get which causal graph is more convincing. And then here we have this data set full of correlation to causation inference, leading to language models, such as either directly presenting them, A correlates with B, can we infer a causation? And then in this case, no. However, if we have this correlation, the answer is actually yes, because if A correlates with B, it means they either have a direct causation or they share a confounder, like a confounding set of variables. C correlates with B, also have the same situation. However, if A is independent of C, then this leads to a causal graph where A and C starts independent and without any commonly shared ancestors in the graph, but B is their common child. And therefore, to make this hold, A must cause B. So to bring this further, although our first work mostly tests LLMs on these direct binary relation distinction, but we do look into future work using our data set or maybe branching out of this to solve the ultimate problem of, in the end, LLMs see a huge pre-training corpus with with different events co-occurring in the same context. And then can they judge what causes what in a future pre-training-like process or fine-tuning process, therefore leading to more robust causal understanding of LLMs. And then the next branch, which we will spend a long time to talk about, is causal effect reasoning. Namely, if we already know the causal graph, how to actually get the quantitative size of the causal effect, which is the main focus a lot of science, including the minimum wage example we posted before. So it started from our CLadder data set on causal reasoning in language models. And basically, we look into cases such as given a set of data, analyzing their correlational statistics might give us information such as vaccinated people are more likely to develop severe cases of COVID in 2021 Israel data. And then we want to answer the numerical question, does it mean that the overall causal effect of vaccination is negative for health? And then the correct way to answer it, as we have already hinted in many examples before, is that we formulate everything in a causal graph. We formulate also the question into an edge. And then we come up with the rest of the causal graph, such as the patient's original vulnerability might be a confounder behind this question, in that the originally more vulnerable group will have a higher vaccination rate and a higher severity rate, namely this variable activating this causal path and this causal path. And then in a certain population, it's totally likely to have a correlation, negative correlation of vaccination and severity. So the right approach here, as many statisticians do, should be to separate the vaccination effect according to different levels of vulnerability. And then, for example, the highly vulnerable people, the intermediate, and the originally very healthy people, and then calculate the correlation of vaccination and severity separately before aggregating them over the vulnerability distribution. So that is the so-called confounder adjustment. We basically look into how language models can achieve this type of reasoning. And we collect all these reasoning examples from famous causality books. And each example in the CLadder dataset is programmatically generated by composing the causal graph, describing the correlational statistics, like a marginal distribution or conditional distribution, and then pose causal effect questions. And then we evaluate whether we also make the data set very comprehensive to cover different types of causal graphs. This one, the way to solve the previous question is by adjusting for the confounder variable. But there are also cases such as we're looking at a mediation phenomena or a collider situation as well. So here, we basically evaluate if a human causal inference scientist can solve this question, then how do LLMs perform? So in the first paper in this series in CLadder, we mostly look into a bunch of different LLMs on this performance, and accuracy is on the yes/no question, so it's up to 100%. where we evaluate both the common LLMs, and also we propose a structured way of leading LLMs to solve these causal questions called causal chain of thought prompting, where we keep the same causal question and all the data provided, but structure the analysis steps into 5 different stages, from causal graph parsing, query formulation, statistics collection, formal causal inference steps, and arithmetics. So I think the causal graph parsing is clear. The query formulation is a bit like auto-formalization in AI for math. We might ask the question of what's the average treatment effect of X on Y, and then that's equivalent to taking the expectation of Y. Suppose that we do an intervention on X, setting the vaccination to true or false. And then taking that difference can be approximated by the confounded adjustment or other methods. And then these methods can fall under categories such as do calculus, where the confounded adjustment is an example of, and also counterfactual prediction, and so on. So Julia Pohl's so-called a ladder of causation, from run 1 association, run 2 intervention, run 3 counterfactual. And bring this further, we really want to even minimize the gap given after our causal COT leading to a boost. So then it leads to our second work in this series called Causal AI Scientist, facilitating causal data science with LLMs. So in this work, we are basically motivated by the same framework, but with a deeper focus on how we structure the formal causal inference steps. So here, this is a domain that many people can do their PhD on. And as mentioned, Julia Pohl also has a Turing Award on probabilistic models, but also a lot of foundations for causality is related to that as well. And then we look into, if we want to further improve LLM causal scientists, how do human statisticians do this data analysis task? So if we look into causal textbooks, we will see many chapters, such as like how to deal with observational data processing, and also how to, let's say, section 7 is our so-called confounding. If there's a confounding effect, then how to adjust for that. 7.6 is what we have mentioned before, and also many other topics in causality. So what we have done is basically turning all these ideas across multiple statistical domains into a whole decision tree for method selection on causality. This is not the full tree, and we just have a snippet here. Let's say if we get a data set from a certain study setup, then let's say maybe the first decision branch is it already a randomized control trial where the mean in difference in means is already the causal effect? And then we can also have a branch that, okay, I cannot do any experiments, such as smoking causes cancer. We cannot do any experiments on forcing patients to smoke or not. And then further, we can maybe look into different other assumptions. One example could be that we can check for temporal information, such as in a certain region, if the tobacco price is suddenly increased, then it will affect the smoking to be more expensive. And then that counts as sort of there's an instrument leading to this change in the population. And then we can further track their lung cancer rate, given the tobacco tax increase. So this is sort of one example of how we can navigate through a bunch of assumptions before deriving at a leaf node that can solve this causal reasoning problem. And then bring this further, as we have covered 7 causal estimation methods and 11 decision steps to fulfill this whole tree to reach a textbook level statistician. And then we further bring it to our whole LLM agentic system, where, again, the user gives a causal query. They give a dataset description talking about this data is collected in a certain way, where each variable means what in the provided dataset CSV file. And then we do multiple steps in this agentic pipeline, from finding the key variables and tagging which one is the treatment, which one is the outcome, given the question, and so on. And then coming up with all the covariates, given the description, plus common sense LLM reasoning. And then, of course, the model needs to deal with problems such as missing values and unclear variable types in a pre-processing step. And then with the clean data, we further go to this decision tree that we carefully crafted with the help of multiple statisticians. And then this decision tree will give us candidate methods. Then we will connect to self-reflection or method validation checks. And also, we will have a coding process to execute everything to Python code before getting the actual, given your study, the causal effect estimate is a certain value, and so on. So we will show this by, actually, let me quickly skip through the other details that we have. But this is the main overview. Some other details is that we basically also follow Bing Yu at Berkeley's theoretical data science framework to have multiple steps from problem formulation, cleaning and processing, data analysis, coding, and so on. And then this will lead to multiple of our studies that started from query, and given the file and description, to parse all the results from the estimated method, the causal effect, and the interpretation. And for example, the minimum wage paper that we mentioned got a Nobel Prize is because they actually did the same process in a very innovative way. Namely, for them to identify whether an increase in minimum wage decrease employment or not, they collect a data actually from hundreds of fast food restaurants right across the border of New Jersey and Pennsylvania. And then there, one of the states actually adjusted the minimum wage, whereas the other didn't. And then to process this natural data that can solve this causal question, they basically come up with the application of the method difference in differences after they collect this data, and compare, let's say New Jersey before the policy and after the policy, how's the employment rate change? And Pennsylvania, how's the employment change, regardless of the policy? And then comparing these two states' trajectory, namely this difference in difference analysis, they confirmed the causal effect size and also the polarity of this causal question. So bring this further, what we have just mentioned is this is not only a skill about common sense, not only a skill about correct textbook level statistician, but it also includes some smart, creative thinking into this, which actually lead us to a separate study that really improves one of the causal reasoning skills in that decision tree in depth. That is the so-called instrumental variables in causal reasoning. And for this one, again, if you see that actually cougar appears in both papers, if we want to look at a certain causal question about does compulsory school attendance affect schooling and earnings, namely longer education as longer education years as a cause and higher wage as an effect to see their relation. And then the thing here is that we have a causal estimation method called instrumental variables. Namely, if we look into kids who are right next to a certain the cutoff of the education, like the same class in the education, the quarter of birth. So this variable affects years of education due to compulsory school laws, but it doesn't directly affect wage in that we don't observe January babies earn more than September people in their later life with a very clear trend. However, this can act as an instrument that modifies the treatment, like changes the education years without impacting the wage, isolating their effect. And then here, the causality bit behind is that we again draw the causal graph and come up with this variable that the researchers think of, which causes the cost variable education, but doesn't affect the wage. And the key instrumental variable has to satisfy a bunch of assumptions, such as relevance of this causal edge and the independence, namely this doesn't exist. And then further, it should be even more exclusive by the only path from the quarter of birth to wage should be through education. So what's happening here is that this causal effect estimation method illustrates 3 skills of causal LLMs. The first one is LLMs as a knowledge base. Namely, we do test, do LLMs recover these canonical instrumental variables, such as this quarter of the birth time, and also, let's say, the tobacco tax, as mentioned before. So we will test abilities to identify well-established instruments in existing economic literature and apply them correctly. The second skill is LLMs as a statistics agent, mainly like proposing valid instrumental variables and check the independence condition satisfaction and so on. And then lastly, we also need it to be creative in that can it come up with cases where, let's say, the babies are just separated by dates that are close to each other, and also the New Jersey, Pennsylvania example is separated by the state boundary. But can it come up with other novel and valid instrumental variables in open-ended scenarios? And then to answer all of them, we not only have the methodological work on having agents that selects the variable and filtering them by common sense, and also checking the actual causal relation by statistical tests, and further adding self-reflection framework into this. Not only do we have this, but also, let me just quickly walk through this, but also we have collected a very precious data set to answer, given the current LLMs, how far are they from scientific level published studies with regard that has the backbone in causal reasoning. So our causal bench, causal science benchmark, basically has around 20 co-authors who all helped us annotating real-world data examples covering 100 data sets and 185 queries from more than 100 papers. And then there are actually realistic data, such as actual employment data and so on, which can have missing values, perfect multicollinearity, unused variables, and so on. As well as to complement that, we have synthetic scenarios also to solve the problem of data contamination with programmatically generated causal relationships and LLM-generated data summary, such as a new data for the same do education years affect the wage later in life, as well as textbook examples from a UCLA study by Kai Wei and so on QR data, where we get 39 queries from education exercises. And they cover a wide range of methods, as we mentioned before as well. Moving further, just to give a preview of what we have in this data set, and we welcome people to follow up. That covers questions from electoral behavior, such as do legislators respond differently by race, healthcare, political economics, and so on. And we also have education questions and even criminology questions and so on. So moving this further, we have then tested our Causal AI Scientist using all these data samples and further published a web app where the users can upload a CSV file, enter the query, and then the LLM in our pipeline go through data analyzer and query intelligence, method selector, and so on before it derives the final causal effect. So basically, we, as is common in reasoning models, our agent also takes a bit of time to select the right method, and also it provides explanation based on the decision tree that has mentioned before. So this explanation, we're working on improving it to the level of the exact snippet in the scientific studies, and hope it can be a causal data analyst for all social sciences, healthcare, and these studies involving causality. So moving further, we also showed that our agent's scaffolding structure has led to clear improvement over different other types of prompting. And I think, let me see. Yeah, the main takeaway before we go to a summary survey paper. So the main takeaway here is that for causal LLM agents, we really treat the problem as a scientist, ground it formally, ground all the information and also the query formally, and design a set of structured steps of how human scientists solve them, and iteratively improve LLMs with tool use, with self-reflection to deliver scientifically grounded results. And we also show the performance on more than 100 real-world studies of causality. So we will quickly skip through this one, but I welcome people to check out. We also have one line of work looking at, with more and more agents adding to the AI for Science pipeline, when does multi-agent debate become better than single agents, and when not? So we will not cover this in this talk, but welcome people to check. And then the sort of concluding roadmap that we're looking at is, what does it mean for AI for science in the era of LLMs? So basically, the bigger picture to enable AI for science include LLM agents automating 5 different components, such as literature review, hypothesis generation, such as like creative cause or creative instrumental variable suggestion, experimental planning, execution by coding agents and so on, and also peer review. And then for our LLM causal studies, we also have a specific roadmap, and we were first motivated by example data sets. So using the same set of causal reasoning, let's say that a very tangible outcome by the end of this year, and maybe with a bit of effort from next year, is that we should be able to process career-related data, employment rate-related reasoning, or maybe each individual talent's profile, and then check what causes their wage and what doesn't. We are also looking forward to moving to biomedical data, starting from the public data sets. Some of them could be, how does air quality affect insomnia, as the UK Biobank would support this query. And further, a stretch goal is to cover chemical experiment data, such as how does temperature affect the reaction yield here, pharmaceutical data on what substance enhances the drug effect, and more domains. So if you notice the order of how I introduce things, they actually correspond to a bigger subject roadmap. The first, so in a 4-step roadmap, the first one actually corresponds to a lot of social sciences. And although we use social science as a label, the fundamental phenomenon here is that it's largely observational data and maybe some small RCTs, let's say, like a large classroom size, small classroom size, like maybe either binary or very small scale RCTs. And then the second step is experimental natural sciences. Let's say that if we do chemistry studies or material science, they are able to conduct hundreds of experiments. All of them are RCTs. And then, but they still need a more effective way to tell them, given all the previous experimental records, what's the effective causal conclusion to conclude, plus what's the effective next experiment to conduct. And then further, my personal interest also spans over philosophy and law. There are a lot of causal argumentation here, like what's the first cause of the world? Given this court case, how to attribute it to the right entity to blame. And then the fourth one on theoretical natural sciences, which might require a lot of skills out of LLM or with the help of LLMs. Like I don't think maybe how Newton proposed his law of physics or how Einstein come up with the thought experiments is immediately achievable with the current LLMs. So I put that as the farthest extended goal to reach. And with this, I also want to thank you to all the workshops that we have organized, plus all the collaborators, mentees, and mentors. Thank you very much.
All right, thank you, Zhijing, for the wonderful talk. Do we have any questions from the audience? Maybe I can ask them while people are getting set up. I'm curious to hear your thoughts on, so for the state-of-the-art methods, how well specified does the structure of the graphical model needs to be in order for these methods to work? So for instance, do I need to specify all of the random variables that are under consideration? Do I need to have somewhat complete data in order for this to work? Do you have any, can you comment on this?
Yeah, great question. So our instrumental study actually lets the model propose a list of diverse variables, but our model also serves like as to do some statistical check. So it's always like it can randomly, no, it can sort of propose things based on LLM's existing knowledge, but we ground it in statistical checks. Then it moves further to the correct causal adjustment methods.
And the random variables are proposed after looking at observation data? The
yes.
models proposed automatically.
So it's both looking at, so I think they're proposed both from observational data and from their own knowledge or creativity. And then we check it, we veto variables based on observational data.
I see.
Yeah.
Thank you. Any other questions? Please step up to the mic, and I can also give you my mic if you're kind of in the middle there. All right, I guess it's getting late in the day. Okay, so thank you again, Zhijing. Please give her a warm round of applause.